So Keshav is a new hire in Aquanty. He's basically just starting now, or this week. Previously, he has done a master's degree at the University of Manitoba in groundwater hydrology and soil science, where he's worked also with Steve Fry, and on using HGS for soil moisture modeling and forecasting. Previously, he did his bachelor's degree in India in agricultural and irrigation engineering, and has worked with a couple of other groundwater models as well. And now he's a junior HGS modeler in Aquanty. And so, yeah, please start your presentation. We are all keen to hear what you've been working on.
Thank you for the introduction, Andre. Good afternoon, everyone. I hope you're all able to see my slides. So, good afternoon. I'm
Yes,
Keshav, and I'm going to present on physical-based hydrological modeling to predict soil moisture in mesoscale catchment in cold climates. Soil moisture is a crucial variable in soil plant atmosphere system. The soil moisture pattern is quite dynamic in nature, and it tends to change due to non-uniform precipitation, solar radiation, and other soil and vegetative properties. It has major influence on crop production and yield outcomes, and it also helps in water resource management. A forecasted soil moisture can help in predicting soil moisture extremes like floods and droughts and other natural disasters. Of many methods which are currently available to measure soil moisture, a physical-based hydrological modeling are the most advanced tool. There are two objectives which I did for the research. The first objective is a comprehensive analysis of the spatio-temporal variability of soil moisture in a subcatchment in Red River Basin by using a fully integrated surface water groundwater model, which is the HydroGeoSphere. Which is HGS. And then another objective was to predict soil moisture over deeper depths in different soil series and analyze the prediction observation correlation for 2021 growing period. The Brunkel subcatchment is approximately 72 kilometers southwest of the city of Winnipeg, and it has the area of 508.96 square kilometers. The figure on the left shows the Brunkel subcatchment with Manitoba Land Initiative as base map, which has 1:20,000 scale, and it has 33 different soil series and 4 observational points. And the figure on the right shows the same Brunkel subcatchment with soil landscape of Canada, which is 1:1 million resolution for with the same 4 observational field, but it has only 5 different soil series. We can see clearly that from the figure on the left, which has the sandy soils are the coarse sandy soils on the west and heavy clay soils on the east. And I did a little bit of field work, which included installing 2 Sentek soil moisture probes for 2020 and 2021 growing season. And there is real-time in situ soil moisture monitoring for agriculture, shortly called as RISMA stations. Especially RISMA stations 4 and 5 are present inside the Brunkel subcatchment. The observational fields for the Manitoba Land Initiative had Crontosol, Scanterbury, and Willowcrest as soil series. And for the soil landscape of Canada, it had only Red River and Rainland soil series. To be more exact, which I'll be going throughout the slides, the Crontosol and Willowcrest and Rainland represents sandy soil series to be easier, and Scanterbury and Red River are representation of clay soil series. There was field work which was conducted during the research by installing Sentek soil moisture sensors and already performed RISMA weather stations, which are specific to Manitoba and Red River Basin, which is present in Manitoba. The Sentek drill and drop probes use soil moisture sensors every 10 centimeter increment till the depth of 100 centimeter. The RISMA stations use hydroprobe sensors at 5, 20, 50, and 100 centimeter depth, which are the usual. And the RISMA stations provide all the climatological data and the observed soil moisture data, which is pertinent for this research. The figures actually shows it's installed in with the data loggers, which transmit the soil moisture data, the soil temperature data to an online field platform called the Field Climate, where I could download all the soil moisture and soil temperature data which was necessary. The figure on the left shows the 3D HGS Brunkill subcatchment model. AlgoMesh was used for unstructured finite element grid. The digital elevation models from the Manitoba Land Initiative define the model topography. The superficial geology was obtained from the processed raster files for the particular transect in Manitoba. The figure on the right shows the 1D model, which is soil column model created for the sensitivity analysis, especially for the soil hydraulic parameters, which influences the soil moisture. The subsurface is only an approximate replica of the 3D model. It is not the exact one. There are a few boundary conditions first considered. The liquid water inflow throughout the model domain, which is the precipitation and the snowmelt, and the potential evapotranspiration. And there was no flow at the base of the model and the perimeter of the subsurface domain. The climate forcing data that were used to run repetitive simulations to achieve the quasi-equilibrium condition and the values of the previous simulation runs were used as the initial condition for the present simulation run. There was quite a bit of data processing which was done for this research. The first one was to collect soil codes from the Manitoba Land Initiative and the soil landscape of Canada and match with the exact soil series which is present only inside the Brunkill subcatchment, which is present only inside the study area. The percentage sand, silt, clay, and along with the bulk density which was obtained from the soil codes from both MLI and SLC was inputted into a software called Rosetta, which uses a single Python script, and it provides the statistical analysis as well. It gives the output data as the Van Genektam and the Mulayam parameters, which are the pedo transfer functions, and they are the residual water content, the saturated water content, the hydraulic conductivity, the inverse of air entry section, and the pore size distribution index as well, and which eventually goes inside the mprops file of the HGS model. The other data processing step was involving the climate forcing data, which I mentioned previously, which was collected from the RISMA weather stations. One, precipitation for the daily temporal time period was easily obtainable from the weather stations, but however, there was a problem getting snowmelt data, and finally it was collected from SNODAS, which is the snow data assimilation system. The figure on the left shows an example day of there was snowmelt during a certain period. Say for example, there was snowmelt. The snowmelt usually happens from March to April and to the beginning of May. And the SNODAS captures a certain spatial extent of only the North America. And I capture only for this Brunkill subcatchment and calculate the snowmelt only for my study area. And next climate forcing data would be the potential evapotranspiration, which I computed manually using the Hargreaves method. And the potential evapotranspiration, most of the input, it involves getting a lot of input factors as well, like the incoming solar radiation, the wind speed and all. But when I decided to get, so the PET was obtained, the weather data could be obtained from the RISMA stations, and also the the incoming solar radiations were obtained from a NASA's tool called the POWER, which is the prediction of worldwide energy resources tool. The final data processing step was to collect data for the surface, like the land cover and the leaf area index. The leaf area index was obtained from MODIS, which is the moderate resolution imaging and the spectroradiometer data. And the data which was available was directly as .htf file. It has to be converted to a TIFF so that a leaf area index for a certain area or the study area could be obtained. Similar to the previous slide, this is an example of a certain day in the growing period where a leaf area index was obtained. but it was done throughout the growing season from 2010 to 2020 time period. And while the spatially distributed land cover factors like the croplands, the wetlands, and the urban area and the water bodies, they were all obtained from the Agriculture and Agriculture Food Canada annual crop inventory. And while the transpiration parameters and time varying root depth were obtained from previous literatures. And all these data of leaf area index, the land covers, and the transpiration parameters goes inside the .et props file for the HGS. This slide will represents the fundamental workflow of how the 3D and the 1D models of the HGS were calibrated. So first, as I said, so the percent sand, silt, and clay of 33 different soil series of Manitoba Land Initiative was inputted into Rosetta, which gives the Van Ginekten and the Mulayam parameters as output. Those Peter transfer functions were used for the sensitivity analysis of soil hydraulic parameters using the 1D HGS model. The 1D HGS model was then integrated with PEST, the parameter estimation tool for the automated calibration. This is an example table of what the Peter transfer functions for 5 centimeter for clay. KOT is an example for sand, and SCY, Canterbury, is an example for clay for the 5 centimeter depth. The results of Rosetta and what are the results of after the automated calibrations were compared, and those data along with the climate forcing data like the precipitation, the evapotranspiration, the snowmelt, leaf area index, which were obtained for all the daily time period from different sources like the RISMA stations and SNODAS and MODIS. They were eventually inputted into the 3D model for 3D model calibration, which was done for 2010 to 2020 time period. Next, after calibrating the 2010 to 2020 model, the 2021 growing season soil moisture data was used for model validation. The climate forcing data were appended manually with the previously successfully calibrated models, and that model was again compared with the values of the simulated HGS model was compared with 2021 measured data, which was obtained from the RISMA stations and the Sentek sensors, which was installed on the fields for both the models. The first slides will only explain the results with time series and the statistical analysis of data. And it will be done only for the graphical representation is only for the 3D models, just to make sure. The time series graph on the left shows the simulated and the observed soil moisture at 5, 20, 50, and 100 centimeter depth, respectively for SCY, which is the clay representation at RISMA 5 stations. The RISMA 5 station had clay soil series, so that is why I'm comparing the SCY soil series with RISMA 5 weather station. The comparison was done specifically for surface soil moisture, which is at 5 centimeter, and for the deepest layers using a technique of volumetric weighted average for the entire 100 centimeter depth. For the current results and all the other subsequent results, 3 statistical analyses considered were the Pearson's correlation coefficient, which is the R, and RMSE, and the percentage bias. RISMA 5 had the clay soil texture, and the SCY soil series, hence they were compared together. This is just a brief description of only the clay calibration results. The range of the simulated soil moisture at the surface were closer to the observed soil moisture throughout the decade, and it was only during the growing season. Throughout 2010 to 2020 time period, the spring season had high soil moisture while it reduced during the winter. The 20 centimeter had the best match between simulated and the observed soil moisture for both 1D and the 3D models. And the soil moisture for the top 100 centimeters showed very good correlations for the 3D model, while the 1D model produced good correlation. However, for the surface soil moisture, both the models underestimated the measured values at the surface. This time series shows the simulated and the observed soil moisture at 5, 20, 50, and 100 centimeters, respectively, for KOT, which is the ground to soil series, which is the representation of sand at RISMA 4 station. The RISMA 4 station had sand soil texture, hence KOT they are compared together. The sand soil showed higher variability in soil moisture patterns than clay, which was obvious in the results. Both models showed good correlations at the surface, while the maximum difference in the simulated and the observed soil moisture was seen at the 50 centimeter and 100 centimeter depth. The volumetric weighted average for the entire top 1 meter produced reasonably good results for the 3D model. However, a weak correlation was observed at the deeper depths. Despite the correlation, the 3D model was able to capture the decrease in soil moisture, uh, decrease in soil moisture from 2016 to 2017, because till 2016, 2014 to 2016 was considered a relatively wetter year, and from 2017 to 2021 it was relatively drier and drought started coming in. Uh, Next will be the examples of the validation results of only the 3D model. The time series graph shows the validated results of SCY soil series, which is the clay on the left, and KOT soil series, which is the sand, which is on the right. Both the 1D and the 3D models were used to forecast, and both the models specific for clay overestimated the measure values at 5 and 20 centimeter depth, while it underestimated at 50 and 100 centimeter depths for clay soil. For the clay soil series for entire 2021 overall, both the models produced fairly good forecasting statistical results with an average PSN's R value of 0.5 for both surface and the overall 100 centimeter depth. And contrary to the clay soil series, which is SCY, the KOT soil series at the RISMA 4 produced weak forecasting results for the overall top 100 centimeter of the soil. And again, the validation results for Sentek sensors which are installed in the field. In order to verify the soil moisture is distributed properly throughout the entire Brunkill model, additional proofs of Sentek soil sensors were installed only for a period of only like 71 days in the field for the growing period for the past 2020 and 2021. The simulated soil moisture in the clay displayed pattern and the trends which were similar to RISMA 5 station, since both had same soil series, which is the SCY soil series. The simulated values for clay showed good correlation for the surface and the overall 100 centimeter depth. However, for the WWC, which is the willow crest sandy soil, very low soil moisture at the range was observed at the surface and the deeper depths. However, the best match between the modeled and the measured soil moisture results were observed only at the sand surface, and poor correlation was observed at overall 100 centimeter depth for the sand. In discussion, the model displayed a variable seasonal transition between the frozen and the thawed states. There was high variability in different soil series where the water content on the soil froze and thawed. 2013 to 2016, as I said, it was relatively wetter years and it had higher soil moisture content, and the transition to the drought condition was seen properly only in the 3D model, and the 1D model was not able to capture that. And of all the period transfer functions, the inverse of air entry suction and the measure of pore size distribution index, which is the alpha and the n, had the largest influence on soil moisture variability at deeper depths, and especially in order to control the soil moisture at much more deeper depths at more than 1 meter below, the hydraulic conductivity, which is the saturated hydraulic conductivity of the subsurface layers, which is below 1 meter depth, impacted soil moisture, which are at subsurface, which are like 50 and 100 centimeter depth. So overall, there was an underestimation of observed soil moisture by the model because of a degree of error in the forcing data, and also because of the use of model data like the SNODAS and the MODIS. Figure on the left represents represents the climate forcing data, which are directly from the weather stations, which happens in real life at the fields. The figure on the right shows the mean precipitation values, which are inputted in each nodes, which will be only half correct, so that the model will only, which will, after the calibration of the model, if only a resultant mean precipitation or the forcing data is applied to the model, it will definitely lead only to an over or the underestimation of the results. And same principle can be applied to precipitation and a potential evapotranspiration as well. Um, there was an important interflow component which was observed in the subsurface, because the shallow geology of Brunkill has the important interflow which was induced in the subsurface water at depths with soil moisture at 20 to 100 centimeter depth, which drains from the sandy soils which are present on the west towards the east along the texture divide, which is the sand clay interface, which was clearly visible. The 1D From the results, it was obvious that the 1D models were not affecting in predicting soil moisture at deeper depths, and the clay soil had at the observations field showed much more validation results for 2021. So, in conclusion, from the research, it was decided that HGS was considered to be a beneficial tool to predict soil moisture at deeper depths in the catchments dominated by clay soils. And the HGS model was able to highlight regional groundwater flows, which influences the superficial soil moisture. And the results which I've previously shared for both the calibration and the validation of the models, definitely it could be improved. They are good, but they are no means perfect because of the little underestimation which led to the dryness of the entire model. Uh, In conclusion, the calibrated model displays good results for the clay soils and reasonable results for sandy soils. The 3D models had slightly underestimated the observed soil moisture values due to fewer limitations, which were previously discussed. The model was able to predict reasonably accurate soil moisture for 2021 growing season, and both the calibrated and the validated soil moisture in clay displayed good correlation at all deeper depths. The sand series did show a good correlation at the surface, but it showed really weaker correlations for the deeper depths. There are few works which are still under consideration for soil moisture, which is comparing the spatial resolution of the soil landscape of Canada, which is 1:1 million, and the entire study, which was Manitoba Land Initiative, which is only 1:20,000. It only shows that there are different polygons having different soil series, and how HGS is able to model soil moisture at different soil series. The model development, since this research, I was able to conclude that it was a good tool for predicting soil moisture for clay soils. So the further development could be done for the soils, for different soils as well. The model comprising a study area covering the entire Red River Valley, which also covers multiple watersheds, bigger watersheds with bigger catchment areas, and also building a forecasting tool by integrating HGS with other prediction systems. So these are my references. I would like to sincerely thank, there are a lot of people from Aquanty who are already involved directly or indirectly for my research. I would like to wholeheartedly thank them, my supervisors, Dr. Sri Fry. Thank you so much for this research opportunity and also for this presentation. Thank you.